We're assuming y is not 0, so the norm is non-zero. But what's this?
1.
Right, that, it has length 1, right?
Yeah.
So we've got the length of y times L of, y over length y. But that is exactly one of these guys, right? So we know that that's 0. So this is length 1, right? So we know when we input anything in, so this is equal to 0. And then of course L of 0 is 0. Consequently, if the norm of L is equal to 0, it has to be identically the 0 function. Okay, so that's one of the things we need for it to be a norm, right? What else do we need? I think the interesting one is the triangle inequality. So how would we do that?
So we need the length of
Oh, what's that? L1, let's,
yeah, L1 plus L2
yeah, well,
is less than,
so okay, a norm of L1 plus L2, let's do that one, yeah.
yeah, and we want it to be less than L1, norm L1 plus norm L2.
Right. So that's going to be equal to the supremum norm of x equals to 1, right? The norm of L1 of x plus L2 of x, right? Which is, certainly going to be less than the supremum of the norm of x equal to 1, and then you got norm of L1 of x, yeah. So by the triangle inequality on the given norm, well, I'm just saying the supremum of that. Like if I take the supremum of a quantity and then I replace that quantity with a larger quantity, point-wise, then certainly the supremum of,
Yeah, but given by definition, wait, but can the supremum be split up?
well, think about it.
Like, do we know that's strictly less than, or, yeah.
Well, we're taking the supremum of the sum of two positive things, right? So anyway, this is basically it. I think you can quibble over whether or not I'm allowed to do these things with supremums or not. But I think you can, yeah. But then why is this? But then these two things separately exist, right? And that's the norm of L1 plus the norm of L2, and there you go, that's the triangle inequality. Let me look in the book and see if he's done anything significantly more, not really. it's pretty much the same. Well, he does, he says that, he says you should look at basically he says that you need to look at the unit ball to make the steps I just made. So he's like, let the norm of x be 1, and then if you look at L2 of x, L2 plus L1, good grief, L1 plus L2 of x, I think, is what he looks at.
He doesn't even use the soup
The norm.
to get from your step 1 to your step 2.
So this is like norm of L1 of x plus L2 of x, like that. He's got this one, right? This is his equation at the top of page 28. I'm working on it. I'm only got to the left-hand side so far. And then he's like, that's less than or equal to the norm of L1 of x plus the norm of L2 of x.
Yeah.
Oh, okay. That's exactly what I did, though. He's just, it's fine. He's just writing this rather than doing what I did, which was just write soup alongside it. I guess you should prove some theorems about the supremum. Like if you've got like supremum plays nicely with inequality, right? If I have a less than b for all variables, input it into A and B, then the supremum of A is less than the supremum of B, you know?
But do you? Like, actually? Because if you think about it, can you say that that's a free, like, could you not just straight up use the triangle inequality, saying that, well, if I know the norm of L1 plus the norm of L2 has to be greater than the supremum of both? Or equal to at the most.
Yeah, I mean, it's by definition equal to it, right?
No, well, what I'm saying is, you have supremum of the length of the norm of L1x plus the norm of L2x. Can't you just say straight up that that supremum has to be less than or equal to L1 plus norm of L1 plus norm of L2? Like, I don't even think you need supremum rules to say that.
The norms are the supremum.
I don't,
Is it right?
yeah, I don't think that's, I mean, I think you have to say that because that's what it means, but, I mean,
That's the definition we gave.
yeah.
I'm mixing up norms.
It's all good.
Yeah, I'm mixing norms up.
So he says the norm defined as we just did is called the uniform convergence norm. All right, and his next theorem says that if E1 and E2 if E1 is a norm space and E2 is a Banach space, then BE1 E2 is in fact a Banach space. So like the next theorem is theorem if E1 is normed linear space and E2 is Banach space, all right, then the bounded linear functions from E1 to E2 is Banach space. So now what would that mean?
And it's any Koshy sequences converging to a value of
Right, we have, in E2, we have that any Koshy sequence converges, right? Any Koshy, yeah, every Koshy sequence in E2 converges to a point in E2. And we don't have that in E1, right? But, so, yeah, that's the next thing on our plate. But I think we're done for today, so I better stop here, yeah? So, yeah, no? You want me? I can do it if you guys want me to. Is it good? You're good? You guys good?
It's okay.
It's okay? All right. Let's try it. Audric, the meeting with my research collaborator,
Yeah.
I pushed it back another week. It would be Friday at your 4:45.
Okay.
And I pushed it.
I do have a race, but I think it's Saturday, so I think we should be good.
Okay. I mean, worst comes to worst, I'll just be back to, you know. Well, I'll be back. So here's the theorem. So we define the norm in the same way I just erased, right? And so all that's left to prove here is that the bounded linear maps from E1 to E2 is a complete space, right? That's what we need to prove. We just argued that its norm exists as we defined it, yeah? So he says let excuse me, Ln be a Cauchy sequence. In here, and he says let X be an arbitrary element of E1. Then he argues that if we look at the norm of Lm of X minus Ln of X, that's less than or equal to the norm of Lm minus Ln times the norm of x. And that goes to 0 as m and n go to infinity. Now, there's a little bit of a fast move right there, because what's he mixing? He's mixing the norm on the function space, right? Like this, you understand the difference here? Like this is the norm in E2. This is the norm in here, which we're just now defining in the last theorem, right? And this guy here is in E1.
Okay, so that's the.
There's a lot going on here, right? So I think that's reasonable. Why? Because remember that the norm of Lm minus Ln, yeah?
Yeah, no, you're good.
It's the supremum, the norm of x equal to 1, right? Of the norm of Lm of x minus Ln of x, yeah? Now, I probably shouldn't even use, let's not even use x here. Let's use z or something different so we can kind of free our mind of it being the same thing that I have over there, yeah? Let's put a z there. Right? So if we look at the norm of Lm of x minus Ln of x, right? We can reasonably assume that, well, if x is equal to 0, this is true, right?
Yeah.
Because this is 0, that's 0, and 0. So if x is not equal to 0, we can rewrite this, right, as equal to 1 over the length of x, the length of x rather, times what? Times the norm of Lm of z minus Ln of z. I could say z sub x if you want, where z sub x is just equal to, x over the norm of x, right? So that makes this thing have length 1. But this is the supremum, right? So that makes this what? Greater than or equal to this thing, right? So we've got this is like that, right? So that's less than or equal to norm of x, right? Times Lm minus Ln. So that's why this is a reasonable thing to write down. see, we have the norm of these images in E2 is bounded by the length of the difference of the operators in the bounded linear map norm times the norm of the input in E1. And because we're assuming that this is a Koshy sequence, that is by assumption limiting to 0. Hence, this is limiting to 0. Therefore, what? What's all this mean? Well, this means we take a Koshy sequence in the bounded linear maps from E1 to E2, and what did we just get? We just got a Koshy sequence not there, but now Lm of x is a Koshy sequence where? In E2. But E2 is a Banach space. So thus, Lm of x converges to what? Well, something in E2, right? And let me follow the book's notation as to not make my life horrible. It converges to 0.
Because we had less than or equal to.
Well, he just says ln of x converges to y. I mean, you're not. Well, this converges to 0. That's true, but that converging to 0 is tantamount to saying that this is a Koshy sequence, because that says that the difference of arbitrary, the mth and the nth term, the norm of that goes to 0, which is to say that that's the condition that's needed for this to be a Koshy sequence. And so then, since E2 is complete, we have ln of x goes to y, and since x is arbitrary element, he says since x is an arbitrary element of E1, this defines a mapping from L from E1 to E2. He says so. Define L of x equal to what are you going to define L of x equal to? Well, you're going to do the limit as n goes to infinity of L sub n of x, okay? I mean, you could slap a y. I mean, you could put an n onto the y if you wanted here. If you wanted to make it seem less like, I mean, that might make me feel better about it. Basically you're saying that's the yn, and take the limit as n goes to, well, I don't know, maybe that. Anyway, this defines L. All right? Then what do you need to show? So we started with a Koshy sequence in the bounded linear maps from E1 to E2, right? We want to show that the limit of that sequence exists in the bounded linear maps from E1 to E2, right? So the calculation he gives is that, here's the main one. So he's like, okay, so ln, the norm of ln is less than or equal to alpha for all n. Why is that?
Because the norm just defines the supremum over the norm of the elements the elements with norm 1. And so using the bounded definition, then it's just the norm of x is 1, right?
Right, that's what he says. He says since Koshy sequences are bounded, there exists a constant alpha such that this for all n and the natural numbers. All right. So let's see here. Then what? So he's like, okay. So then let's look at the norm of Lx. That is equal to the norm of the limit as n goes to infinity of ln of x. All right. Which is he says that's just less than or equal to alpha times the norm of x. Because we have that is, so he's using he's using this thing up here again, right? Because you've got, I mean, it's again this, right? You notice that you've got this, the norm of ln of x, right, is less than or equal to the norm of ln times the norm of x, yeah? By that logic that we went through up here. We can still do that again here. But now we also know that that's less than or equal to alpha, right? And if that's true for each n, then taking the limit, then if we sort, yeah, right, this is less than or equal to alpha times the norm of x, which then says what? L is bounded, right? L is bounded. And he says it remains to prove that ln minus, he says it remains to, so like we've constructed this function, right? But we haven't proved that that is the limit of our sequence either. So it still remains to prove that this function that we're looking at, which is apparently bounded, great, but we also need to prove it is in fact the limit of the Koshy sequence that we began with. And so that's what's left to do here. And let's see here, how's he do it? It's about 4 lines here. I don't think it's anything terribly deep. I can write it down if you guys want. See, let me write it over here. Any questions, Audric? Or?
No, I'm still following.
Cool. All right, so let's see here. He says let epsilon be greater than 0 and let k be a natural number such that the norm of Lm minus Ln is less than epsilon, right, for Mn. Why can we do this? Yeah, we're assuming it's a Koshy sequence, very good. And then he says, if the norm of x is equal to 1, and m and n are such, greater than or equal to k, then the norm of Lm of x minus Ln of x is less than or equal to the norm of Lm minus Ln. Right? I mean, okay, so we're again using the calculation that I pointed out. It's again this, which I really feel like that should be a lemma before he does this thing. Anyway, so this is times the norm of x, right? But the norm of x here is by assumption 1. So this is straight up less than epsilon, right? All right. And he says, by letting n go to infinity, holding m fixed, what do we get? He says we get that the norm of Lm of x minus L of x, right, is less than or equal to epsilon for m greater than or equal to k, and each x in E1 subject to what? Yeah, with norm of x equal to 1. And that means, so that says, he says, that means that the norm of Lm minus L is less than or equal to epsilon for all m greater than k, and that proves that the L is the limit of our sequence of operators. So yeah.
Sorry, how do we get to the last?
Oh, this last step?
Yeah.
Let's see here. So remember the norm, this, right, is what? This is defined to be the supremum of the values of this operator on the unit ball.
Okay.
But we know that a bound of the values of the operator on the unit ball is epsilon, so that makes this the supremum less than or equal to epsilon. But since epsilon is arbitrary and this holds for all m larger than k, that proves that, you know, the limit of the sequence L sub n is L.
Goes to L. What's the same?
We can make it as close to L as we want by taking m sufficiently large, is what this means.
No,
And there you have it. So the bounded linear maps from E1 to E2 is, as we claimed, a Banach space. So yeah. Yeah, go for it. And so this operator norm that we're working with has come up, like when I've studied advanced calculus before, you want to prove things about, like, you know, the derivative or something, multivariate derivative. This comes up because you end up wanting to take, like, the norm of a linear map. And how do you define the norm of a linear map? You see, you don't know that the linear map is on a finite dimensional space like it. Well, anyway, I've run into this operator norm in the middle of proving things for advanced calculus before that don't seem infinite dimensional. But anyway, enough. You guys have done enough for today. So yeah, Audric, we